Hello, and welcome back to the course on University Physics 3. So we are now on the ninth chapter for this course, which will focus on electromagnetic induction. So before we proceed with the first lesson, let us first review some topics. So when we discuss about magnetism, we discussed in passing about the magnetic flux, which is just B dot dA. So when we discuss about the Gauss law for magnetism, we actually took the closed surface integral. So there's a closed surface integral there. But if we only focus on the magnetic flux, it's just the integral of B dot dA. So since this is a dot product, then it's B dA cosine phi, where phi is the angle between B and the area. And if your magnetic field and your angle phi does not depend on dA, then you can take them both out of the integral and you will be left with integral of dA, which is just the total area. And the magnetic flux simply reduces to B, the magnetic field, A, the area, cosine the angle between them. We also have discussed about current, resistance, and EMF and Ohm's law. So if you have an ideal source of EMF, then the voltage is just equal to the source, to the EMF, and that's equal to the current times the resistance. So for the first lesson of this chapter, we will be talking about two laws involving electromagnetic induction, and these are Faraday's law and Lenz's law. So in the 1800s, there are electromagnetic induction experiments carried out by Michael Faraday separately in the UK and Joseph Henry in the US. So what they did is they have a magnet and they have a solenoid or a coil of conducting wire. And they connect the coil of the conducting wire to a voltmeter. And they noticed that the needle in the voltmeter, or there is an EMF induced in the coil whenever the coil moves with respect to the magnet, or the magnet moves with respect to the coil, or the area of the coil changes, or in general, since the magnetic field and the area combined both describe the magnetic flux. So whenever the magnetic flux through a coil changes, then there is an induced EMF and there is an induced current. So the induced EMF is given by negative n. N is the number of turns in the loop, and d phi dt is the change in magnetic flux with respect to time. And this is what we call Faraday's law. So the Faraday's law states that the induced EMF in a closed loop equals the negative time rate of change of the magnetic flux through the loop. So basically, this is our general definition of the magnetic flux, integral of B dA cosine phi. But again, if your magnetic field doesn't depend on the area and your angle doesn't depend on the area, then this will just reduce to BA cosine phi. So the flux is maximum if the angle between the magnetic field and the area vector is 0, or both are parallel in pointing in the parallel direction. So take note, the area vector is always perpendicular to the surface area of the loop, and there is 0 flux whenever the area vector and the magnetic field is perpendicular to each other, since cosine of 90 degrees is 0. So Lenz's law, if Faraday's law is for determining the magnitude of the induced EMF, then Lenz's law is for the direction. So Lenz's law states that the direction of any magnetic induction effect is such as to oppose the cause of the effect, and that is actually the negative sign here in Faraday's law. The negative sign here describes the direction. So when you say negative, it's always the opposite opposite the cause of the effect, opposite the change in flux. So if the flux is changing in this direction, then the induced EMF is in the opposite direction. So this implies that nature doesn't want magnetic flux changes. So if you change the magnetic flux in a coil, then nature will actually counteract by giving a back EMF. So for example, in this scenario, you have a loop and the area of the loop is fixed, but the magnetic field is increasing in that direction. So meaning, in order to oppose Faraday's law and Lenz's law, both states that the induced EMF and its direction is such as to oppose the cause of the effect. So if the effect is increasing, or if the change is increasing, therefore there will be an induced magnetic field in the opposite direction. So if the induced magnetic field is in this direction, then the direction of the induced EMF and induced current is in this direction. So that's right. So let's have other examples. So for example, in the first case, you are actually moving the magnet closer to the loop. So since this is the north pole here, the direction of the magnetic field is in that direction. And the direction of the magnetic field for a north pole is actually in this one. It's actually downwards. So, and it's increasing. So therefore, there should be an induced EMF upward or going up to oppose the increasing magnetic field that is downward. Now, in this example, the south pole of the loop is facing the loop. So therefore, the magnetic field of the magnet is upward. But you are actually moving the magnet upward. So it's going far from the loop. Therefore, the magnetic field is decreasing. The magnetic field is in that direction, but the magnetic field is decreasing. So therefore, there will be an induced EMF to support the decreasing magnetic field. So, and it will be in this direction. So the induced EMF will be in this direction. So the current will move in that direction, so in this direction. So similar with example C and example D. Okay, so let's now have an actual problem. So the magnetic field between the poles of the electromagnets. So you have an electromagnet. These are basically coils of wire there, solenoids, is increasing at a rate of 0.020 Tesla per second. The area of the conducting loop. So you have a loop placed between the poles of an electromagnet. This is the north pole, this is the south pole, meaning the magnetic field is upward and it is increasing. So the area of the loop is 120 centimeters squared and the total circuit resistance is 5 ohms. So find the magnitude of the induced EMF and the induced current in the circuit. If the loop is replaced by one made of an insulator, what effect does this have on the induced EMF and induced current? Okay, for letter A. So the induced EMF is just negative N, change in flux, change in time. Now, the flux here, in this case, so the magnetic field and the area vector is actually in the same direction. So cosine of 0 is 1. So it's just B times A. So if you take the derivative of B and A with respect to time, since magnetic field is constant, you can take it out of the derivative and you will get the area is constant. The magnetic field is actually changing, so you can take out area out of the derivative. So NA, and then you will have dB dt. And since there's only one loop, so N is equal to 1, so you will just have negative A dB dt. Okay, so the area is 120 centimeters squared. And if you convert that to standard units, so you multiply that by 10 to the negative 4. dB dt is actually increasing, so it's positive. It's 0.020 Tesla per second. So this is meter squared. This is Tesla per second. So your EMF will be negative 0.24 times 10 to the negative 3 or millivolt. So that is your induced EMF. So again, the negative sign pertains to the direction. So the induced EMF, the induced magnetic field, in this case actually is in the opposite direction of the original magnetic field. That's what it means by the negative sign here. If you obtain a positive sign here, it means the EMF, the induced magnetic field is in the same direction as the original magnetic field. So meaning it's opposite. The induced EMF is downwards, and this is the direction of the induced current. So to solve for the induced current, so induced current, let's just take the magnitude. It's just the magnitude of the induced EMF over. So you have 0.24 millivolts over the resistance is 5 ohms, and you will get 0.048 milliamperes. 0.048 milliamperes. That one. So that's for letter A. So for letter B, if you replace the loop with an insulator, so if it's an insulator, then current will not flow through an insulator. So current is 0. So the EMF is still the same, 0.24 millivolts, but the current is 0 because the resistance of an insulator is very, very large. So I, since I is EMF over R, if the resistance is very large, no matter what is your EMF, if the resistance is very large, insulators have very large resistance, then the current is very small or approximately 0. Okay, for the next example, we have a coil of wire containing 500 circular loops with radius 4 centimeter is placed between the poles of a large electromagnet, where the magnetic field is uniform, so constant magnetic field, and the angle is 60 degrees. Okay, so the field decreases. So again, the magnetic field is uniform in direction, so but it is decreasing. Its magnitude is actually decreasing at a rate of 0.200 Tesla per second. So what are the magnitude and direction of the induced EMF? So in this case, our flux, magnetic flux will be BA cosine phi, where phi is actually this one, 30 degrees. It's not 60 degrees. Again, phi is the angle between the magnetic field. So magnetic field is in this direction, to the left or to the right. And your area vector is perpendicular, 90 degrees with respect to the surface of the loop. So this is the side view of the loop, okay? This is the area vector. So the given angle is that one, 60 degrees. So therefore, the angle between the magnetic field and the area vector is 30 degrees. So P here is 30 degrees. So area again of the loop is constant. It has a radius of 4 centimeter. Phi is constant. So therefore, the magnetic field is the one that is changing. And from our formula, and derivative of the magnetic flux with respect to T, so you can take out A and cosine phi, and you will have dB dt. So the derivative of this with respect to time, only B is the one that is changing with respect to time. Okay, N is 500, area is pi times radius squared. So the radius is 4 centimeter. In terms of meter, that is 0.04 meters squared. So pi r squared, that's the area. Cosine of 30 degrees. And dB dt, take note, decreasing. Decreasing is a negative change. It's negative 0.200 Tesla per second. So that one. So if you calculate that one, you will get a value of 0.435 volts. Okay. So the answer is 0.435 volts. And the direction of that, since it's positive, meaning the induced EMF is actually in this direction, in the same direction as the induced magnetic field. So actually in the same direction as the area in this case. So the direction of the induced magnetic field is in this direction. So therefore, the current and EMF is in this direction. Meaning, at this point, the current is out of the page. So it's a dot. And this point, the current is into the page. So it's an X. And at this point, the current is upward. The current is into the page, goes up, and then out of the page. So that is the direction of the current and the induced EMF. Again, that means out of the page, cross means, that means out of the page, cross means into the page. Okay, third example. So this is an alternating current generator, which is also called an alternator. So an alternator is a device that generates alternating EMF. What is the induced EMF at any time when the coil is rotating at a constant angular frequency omega? So in this case, there are actually magnets in between here. There's a north pole here, there's a south pole of a magnet here. So the magnetic field is in that direction, to the right. And the area of the loop is actually fixed, but the loop is now rotating. So you will notice that the angle between the magnetic field and the area vector is actually the one changing in this case. Okay, how do we find the induced EMF? So this is the plot now. This is the plot of the. You will also expect, since our phi, the angle between the magnetic field and the area vector is changing. Actually, it's periodic. It repeats from 0 to 360 degrees, or 0 to pi. So it's oscillating. This means that the induced EMF, the flux is also oscillating. So this is actually the flux. And the EMF will also oscillate. So it will have a maximum value, it will become 0, it will have negative value, it will become 0. So it will wave, it will oscillate. Okay. So the EMF is just negative N, change in flux over change in time. And our magnetic flux is BA cosine phi. B is constant, A is constant, phi is not constant. So from your lesson in mechanics, the angular displacement is just equivalent to phi naught plus omega naught t plus 1/2 alpha t squared. This is actually our equation. We will assume that the initial angle is 0. And since this is only rotating at a constant angular frequency omega, this is actually our omega. I will no longer put not. So it's not accelerating, it's not speeding up, or it's not slowing down. So there's zero acceleration. So it's just omega t. So basically, our phi is just equal to omega t. So phi is just equal to omega t. Okay. So you take the derivative of this. So basically, you can take out b and a out of the differentiation. And n is just equal to 1. So you have negative ba. Then derivative of cosine omega t with respect to t. So the derivative of cosine is, of course, negative sine omega t. So you have negative sine omega t, derivative of omega t with respect to t, so omega. So you have omega ba, and then sine, negative sine omega t. So there's negative, there's a negative. So the EMF will be omega ba sine omega t. So you will notice that the EMF will actually oscillate, because sine is if you have a sine sinusoidal function, so it will oscillate with time. So at this time, this is the EMF, at that time, that is the EMF, so it actually oscillates. It's an oscillating EMF, so therefore it will generate an oscillating current, or what we call an alternating current. An oscillating current is an alternating current. So in this case here, the EMF is time dependent. It depends on time. So there's no exact value. So in commercial alternators, many loops of wire wound around a barrel-like structure such as this one. So the magnets, the electromagnets are actually the one rotating instead of the coil. So that is what a commercial alternator looks like. So your cars have alternators, your motorcycles have alternators. So that one. So I guess this is the last example for this chapter. So this is what we call a slide wire generator. So you have a conducting wire shaped in a like a U, and then you have a movable wire here on top of the conducting U-shaped wire, and you expose this to a magnetic field. So in this case, the magnetic field is into the pitch. Now, if you move this wire here, say wire with length L, if you move it with a velocity v in that direction, what will happen is area of the loop will actually change. So this is an example of a changing area. So if you move this wire here in that direction, so the area of the loop is actually changing. So what is now the induced EMF for this case? Okay, let's again start with Faraday's law. It's negative N, change in magnetic flux with respect to time. So the flux in this case is actually just B times A, since the magnetic field and the area is in the same direction. They are into the pitch, and the area is actually the width times the length. So the length is constant, but the width is actually changing. So basically, the flux is just B times the width times the length. Okay. So N is just equal to 1. This is just one loop, so they have negative. So B is constant, L is constant, so you have BL, and they have dW dt. So the width is actually the one changing with time. So the rate of change of the width with respect to time is actually given by this velocity. Change in length or change in width or change in time is actually just the velocity. So you have, this is V, the velocity, negative VBL. Yeah. So there will be an induced EMF in this direction, and its direction will be clockwise. So if you will recall, so I will just be discussing this in detail in the next lesson, because this is the lesson called this is an EMF called a motional EMF. So I will discuss this clearly in the next lesson. So again, the negative sign here implies that the induced EMF is in the opposite direction as the area and the magnetic field. So the induced EMF in this direction is out of the pitch. So the EMF and the current is in this direction. It's counter clockwise. Okay. So I will discuss more more deeply regarding the last example, example number 4. I will discuss that more deeply and clearly in the next lesson, which is all about motional EMF. So I will see you again in the next lesson.